All right. It's 7:05, so I guess we'll go ahead and get started. Okay, cool. Now we're good. Okay. So today we're going to be talking about communication and pathfinding. So I'll be starting to talk about communication. My name is Pranali. And Jerry and Ian over there are going to be talking about pathfinding later. This is a very important lecture today, guys, because communication is a huge part of this game and pathfinding is an even bigger part of this game. So yeah, glad you guys are here. Tell all your friends they're really missing out. Yeah. Okay, so let's get started. So this is just like from the spec, so most of you guys should know this. So the shared array, there's one for each team, and this shared array has 64 different slots in it. And the max value we can write to that shared array is 2 to the 16 for each of those slots. Another thing to consider is that reading is going to be cheap within this array, and writing is going to be a little bit more expensive. So writing to the array is costs you 75 bytecode versus reading costs you 2 bytecode. And maybe we haven't thought too much about bytecode yet so far in this lecture player series, but today we're going to start thinking about it a little more, and we're going to continue that next week. And then also we have these additional problems this year where we can only write when we're within 20 units of an amplifier, within 4 units of a headquarter, or within 9 units of a captured island. Cool. Okay, so the first thing let's talk about is how do we store a location? In a lot of cases, we're going to want to store a location. For example, we might want to store the location of a well, an island, some of your bots. But regardless, locations are going to be like a really important thing to store. So I guess like one of like the most like straightforward ways to store a location is going to be to take 2 indices for a location. So we can store that like mapLocation.x in one place and mapLocation.y in the next index. But as I'm sure you guys can kind of think of, that there's definitely better solutions to this, and you can kind of see on my slide, I'm giving away a lot of information here. But so we can see that a better solution might be to like number the blocks like this. So we have like 0 in the bottom left and then go all the way up to 8. So now why does this work? I guess you guys know like what is the max size our map can be? Exactly, 60 by 60. So that gives us like a total of 300 or 3,600 values, right? And 3,600 is less than 2 to the 16. So we can still store it all in one index. Yeah, does that make sense to everyone? Cool. Okay, but then since we have 0, like one of our map locations is 0, 0, and that will amount to 0 when we're doing like just like map width times y plus map x, right? So an even better solution is to reserve 0 to represent unused array indices. So this means that we can easily read through our array and see which ones are not being used and which ones are being used. So then we can start by representing 0, 0 is 1, and then go all the way up. So we're still preserving that same information. We're just adding 1 to every value just to make sure that we can easily tell if we're using that array index or not. Cool. So what kinds of things do you think would be useful to store in our communication array? Anyone have any ideas? Guys, this is a lecture about communication. Let's communicate here. Come on. Well positions? Okay, that's a great one that I might not have actually done. But, you know, cool. Headquarter positions? Yeah, headquarter locations. Okay, great. So honestly, it's up to you. Like well locations might be a great thing. I think that's like probably a great thing to add to your robot. But today we're going to focus on headquarter locations, island locations, and some ideas of like how to store enemies. But these same ideas, like how we're going to store these things, they can definitely be extended to other elements. So definitely that's something to integrate into your own robots. Okay, so let's start by talking about headquarters. So this is easy. Let's just write our own location on turn 1. And important to note is that headquarters can always write their own location, since you have to be within a certain distance of a headquarter in order to write. But I mean, headquarters naturally are next to themselves, right? So yeah, this is a pretty easy first step, but let's do it. Okay, so this is going to be a pretty long lecture. So I started by writing out some things for us. So first we can see that we implemented this location to int that we talked about earlier, where basically, I don't know how to hide this better. What, like always hide for me? maybe, okay. So in location to int, we have if m equals null. So that means like if our map location is null, we return that 0 that we talked about. And otherwise we do just like 1 plus the mx plus my times get width. And then the same can be reversed into location. Cool. And then another thing we're going to add is like this add headquarters. So I also went ahead and implemented this earlier, but it's a good thing to just look through. So we can get our own location, and then for int I equals 0, we can go ahead and like get the game constant's max starting headquarters. And for each of those, we're going to read the shared array. And if the shared array is 0, right? So we're saying that the reserved value of 0 in our shared array means that it's not been used yet, right? Then we can write to the shared array. So we don't want to overwrite information. That's why we're making sure it's 0 before we write to it. And then once we write once, we can just go ahead and break that there. So then each of the headquarters will call this on like turn 1. And once they call this, they will all write their locations to the shared array. Now, we can then go into the shared array on turn 2 or turn anything that's later than 1, right? And we can figure out where our headquarters are. So we can say like if robot player turn count equals 2, we can say, okay, let's go through all like the headquarters and just go ahead and write them into our own static memory, right? So yeah, then all of our robots now know where all of our headquarters are going to be, and that's going to be potentially important for your future logic. Everyone good with that? Yeah, cool. Okay, awesome. Okay, so let's go continue the lecture, I guess. So let's get a bit more complicated. So let's talk about storing islands. So first of all, where can we store our islands within our array? Does anyone have any ideas? Like how much have we already used? Yeah, that's right. We've used 4 elements because we have a max of 4 starting headquarters. So great. So we can start at index 4 and we can start using storing all our island information since it's 0 index. And then, so do you guys have any ideas about what we should store about our islands? Location. Ooh, I like location. I think that's a good one. And I think, honestly, maybe this is something you guys want to consider for yourself in your own bot, but I think we don't need to store every location within the island, right? We can maybe just store like our nearest location of any island we've seen, right? And this is where our logic about where our headquarters is going to be useful to figure out the nearest location of any island. Okay, now we've encountered a new problem. We're not always in range to write this information to the shared array, right? Sometimes if we're like a carrier and we've wandered away from the headquarters, we can no longer write to the shared array. So do you guys have any ideas of how we might want to resolve this? Great. Yeah, let's add a queue. When we are in the range, we'll just go ahead and write to our shared array. And when we're not in range, we'll just push it to the queue and then we'll see what happens. We'll write it later on. Some things to consider about this queue is some of our information might get outdated over time. Now, do you guys think this is a problem when we're storing the location of islands? No? Okay, why not? Yeah, the islands don't change locations. So great. So we don't really care if that information is outdated, right? But some of the other information we're going to write in the future might become outdated. So we can talk about that when we get there, but it's like, we don't really care about it here. Okay, so time to go back to coding and let's store some island information. Okay, so I guess here first, let's create our queue. So I also went ahead and coded this, and here we also have like if the or actually, yeah, let's start with updating island info, right? Okay, so for an island array, right, we're just gonna say or for the island ID, we're just going to say like RC can or sense island nearby island locations. and we'll just give it null and a radius squared of -1, and that's the ID. So we know this will give us all the map locations. Okay, and yeah, again, we're not going to go through and like store the nearest one in this case. We're just going to store like the first one, but the code I released tonight will have it as the nearest one, so you guys can use that. But let's just say like, okay, so if island locations dot length is greater than 0, let's just okay, so now where do I need to write to my shared array? Where should this island go? Yeah, so we're gonna want it to go to the ID plus the starting island index, okay? And the starting island index in this case is going to be 4, because as we said, we have a max number of headquarters of 4, right? So then we can store all the islands after that in like consecutive fashion, right? Another thing to consider is that we know that the IDs of islands are consecutive, and they range from 1 to 35 max, since we can have a max of 35 different IDs. So that can tell us that we can just write straight to the index of ID plus starting island index. You guys might want to subtract 1 here later, just because our IDs for islands do start at 1, but for now we're just going to leave it as that. Now, what do you guys think? Should I just go ahead and do can write shared array with ID and location to int RC island location 0? Does that seem good? Oops, this is index to right. Does that seem good to you guys? Yes? Okay. Why is this not necessarily the most efficient? We might have already written something about this island in the past, right? Why are we overwriting it if we don't necessarily know we are getting more information? As we talked about earlier, writing is going to be very expensive in terms of bytecode for you here, right? So we want to read first, and we can use our reading very freely since it costs just 2 bytecode. So we want to minimize our writing, and it's fine if we have to write in order to achieve that. So instead, let's just go ahead and say like the value we're going to write is going to be this value, right? Okay. So if value is not equal to RC dot read shared array of the index. Can you guys all see this, by the way? I will take silence as a yes. Okay. I guess, does this make sense to you guys? Why we're choosing only to write it if we aren't reading the same value, so we have new information to add? You guys probably want to formalize this check, and I think this check is formalized in the code I'll release, but it's basically going to say like if we have a closer island. Yeah. Okay. Perfect. Yeah. So now let's talk about other things we could store. So let's talk about storing enemies. So when you see enemies, you might want to store where they're located. But it's going to be really expensive to store every location of every enemy that you've seen, right? Because, I mean, your enemies might be really good. They might have like hundreds of bots, right? We don't want to fill up everything we have, right? So instead, let's keep track of the approximate locations. We can also use this information because we think that enemies will probably roam together, right? So if we see one enemy and we see other enemies around that, we see that there's a cluster there, and then we can like go to that cluster is kind of the idea here. So then we can just store it as an unordered list of location integers. And then, yeah, so how this is going to work is that we can report an enemy. So we're going to report that enemy if the, so you add the location to the array, if it's not part of an existing cluster or if there is an empty slot. So for example, we can check if it's part of an existing cluster just by going through and reading the different clusters that exist and seeing how far it is from a cluster. Again, here we're making use of the fact that reading is not very expensive to us, but writing is, and we want to minimize how much we write to the array. Do you guys have any ideas of what you think good cluster sizes could be? Yeah, I agree. I think the vision radius is a great cluster amount, because if we can see our vision radius, then we'll see all the enemies nearby us, right? And also, I think vision radius is going to be the same this year for launchers and carriers, so it's extra helpful. Cool. We also want to clear obsolete enemy locations. Importantly, as we saw in the previous slide, we're not going to write if we have no more space in the array. So we need to make sure we're clearing out obsolete enemy locations so that we can continue to write to that array. So for each enemy location stored, let's delete it if the robot can see that location and there's like no enemy within, again, like that vision radius, something like that, right? And maybe you guys can like formalize this, add some more conditions. And we also want to run this before we start reporting the enemies so that if we do see any enemies, we can put it in that array, right? Okay, cool. So let's go ahead and code this part. Okay. So to clear obsolete enemies, how are we going to do that? So like, where do we want to start going through our for loop or through our communication array? Yeah, so similarly to how we have like a starting island index, we can have the starting enemy index, which tells us like what is the first value that starting enemy index can come from, or the first place where enemies can be stored. And that's just going to be based on like how many things we've stored previously. So since we've stored the first 4 values in our array are the headquarters, and then the next like 35 maximum are islands, then we can start storing our enemies after that, right? So yeah, we can just do that, right? Is less than, and then we can just go ahead and store to the end of the array here. So game constants. Okay, and then we can read the shared array to get okay, I don't know. It's probably not super helpful if you guys just watch me code. So we'll just assume that does everyone is clear on how like clear obsolete enemies would work? Yes. Okay. And how about like report enemy? We like understand what's going to happen in that case. And then get closest enemy based on these 2 values, right? We can just go ahead and go through that shared array. And that's an example of how we're going to start using the shared array to enable our bot to have like more complex logic. And you'll see that as we come up to pathfinding pretty soon. Cool. Okay, then yeah. This code will be released, as I said, after this lecture. So we'll just continue to go through it. Okay, so the next thing is bit hacks. We're going to use bit hacks to encode more information. So let's see. How many of you guys have seen bit hacks before? Okay, nice. A couple. Okay, cool. So the idea here is that 2 to the power 16 is this large number, 65536, right? And we so that gives us 16 different bits to work with within that integer, right? And as we one of you guys helped me out earlier and said, there are 3,600 possible map locations at maximum, right? So in that case, we can use those extra bits for something else. We can represent more information here, right? So let's talk a little bit more about like how these bit hacks can work. So for example, in these 16 bits, we can hold two different numbers that range between 0 and 255. We can also hold like 16 booleans that range between 0 and 1. We can also like break this up unevenly. We can store a boolean and then like some numbers. We can also like left shift. Yeah, and then these are the operators that we're going to use a lot for bit shifts and for bit hacks in general. So we can left shift, which is just going to be like basically multiplying by 2 and adding zeros at the end to the least significant bits. And we can also right shift, which would just be like basically dividing. So we're just like moving it over. So let's see like kind of an example of that. Okay, cool. So like, let's say we want to write both the number 51 and 129 and store it all within one integer, right? So we can go ahead and write 51, and then we can bit shift it left by 8 bits, right? So now we have 8 bits free that are our least significant bits that we can add 129 to. And now this final value is 130 or 13,185, which doesn't mean too much by itself. But then we can go back in, and when we read, we can bit shift it right 8 bits and then read the least significant bits to get out 51. And then we can also read those most significant bits so that we can get the original least significant bits to get 129. I guess, is that making sense what these bit hacks are? Cool. Okay, so let's use an example of bit hacks to encode more information about our islands. So currently we talked about how we're storing location, right? And as we talked about, we have a max size of 60 by 60. So we're storing 2 to the 12 bits there maximum, right? So we have 4 extra bits, which we're wasting. Let's add some more info to that. Okay, so what kind of more info we could add? Maybe we could add who owns the island. How many bits do you guys think it would take to store who owns the island? 1? Okay, cool. Tell me about why it's 1.
Because it's like a boolean, like either you own it or the other.
Yeah, okay. I think you're right. You're really on the right track, but like there's something a little weird about this because we have that team neutral, right? We want to know also when an island isn't being owned. But you're absolutely right. Okay. And then another problem is that the health of the island, right? So then we're going to have 3 bits left if we store the island in 1 bit. So then we can store the health of the island, but we can't fully store this information because the health of the island could be up to 750, right? I claim though that maybe we don't care about all of the island health, right? Maybe we don't only care about like the scale of the island health. Maybe we only care if it's like a small amount, or maybe we only care about the difference. Maybe you only care about if you have a lot of robots on it, right? So that's a little bit more for you guys to decide again, but we're gonna go ahead and just like scale down the island health here to represent that. And now let's come back to the question about how many bits it would take to see who owns the island. So if we are only looking at the information about 1 bit to see who owns the island, it's not enough to tell if it is one of the 3 options of neutral, team A, or team B, right? But instead we can combine this with the information about the health of the island. If we know that the health of the island is above 0, and we know that the bit set about who owns the island is like one of the other, we know that if the health of the island is non-zero, that the island cannot be neutral, right? And similarly, if we know that the health of the island is 0, we know that it doesn't matter what's in our bit about who owns the island must be neutral. Is that clear to everyone? Cool. So because of those 2 pieces of information being intrinsically related, like we can store the information together. Oh yeah, okay. So now let's talk about how we can code some bit hacks. Okay. So we can add this like bit pack island info function. Okay, so I guess like let's assume that we're given the closest location for the island info, right? So let's start by changing that. Okay, so now what do we need to do to the island in order to store the location in the top 8 bytes? Or the top 8 bits? Yeah, okay, so we can just like merge, or sorry, the top 12 bits, my bad. Okay, we can just like shift it over by 4 here, right? So we can also use, I defined these constants earlier, so the total bits we have is 16. The math block bits we need is 12, the team bits is 1, and the health bits are going to be 3, right? So we can shift it over by total bits minus math block bits. So that will shift it over by 4. And then that's going to put these math location bits in the top 12 bits that we have in this integer. Does that make sense, everyone? Cool. Okay, so now let's store the next thing we need to store, right? So let's say we want to get the team holding the island, right? So we're just gonna do like rc.sense team occupying island ID. Okay, and then let's just quickly look. So here that we see that team A is here and team B is there, right? So we can just go ahead and do like ordinal. So in island plus equals team dot ordinal. Okay, does that look correct to you guys? Yes? Are you sure? No? Okay. Yeah, I think I need to like we need to still go up with team ordinal, right? Like we still need to bit shift it left. We can't just put it at the bottom because we already shifted it island with like up, so it's at the very top. So we need to do team ordinal. And how much am I going to left shift this? Sure. Go for it.
3.
Yeah, exactly. So we're just going to shift it like the number of bits we're reserving for help, right? Cool. So now we can finally do health, which is just going to be like there we go. Okay, and now you guys have stored like a lot more information in here than you have previously, right? And also this shouldn't be exactly health because as we talked about, we're going to round it. So I think we're going to do something like health divided or and we probably talked about this earlier, but make sure you guys remember that in Java, we're going to be using integer division. So that's why I had to convert this to a float here before I divided it. And we're just going to ceiling it. And why we want to ceiling it here is because we want to ensure that even if we have 1 health, that it's represented as some health in order to use that trick that we were talking about earlier, where we can tell who the team is based on if the health is 0, right? So if we just did a straight integer division, a health of like 2 would be represented as 0. So then we would think the team is neutral, but the team isn't actually neutral. They just have a low health. So we're going to do that here. Yeah, feel free if you guys want to change this code later, but that's what the lecture player is going to have. And then let me just catch my exception really quick. Okay. And return the end here. And here we can just like return in island outside so that it's still bit packed, but not perfectly. Okay, cool. So now we're gonna also like figure out how we can like read that same data from this bit packing, right? So I went ahead and started implementing read the team holding the island here. So I guess could anyone help me like explain what this code is doing here? I can expand it a little if that would help. Yeah, okay. So we're getting like the island ID, right? And then we're reading the shared array. Then we're creating this bit mask. So this bit mask here is just going to be like so 0B just means that we're like using binary here and we're doing 111, right? So that means each of our least significant last 3 bits are going to be ones. Now we can do this. I don't know if you guys have seen this notation before, but remember and in Java is and. So this is not a normal and, this is a bitwise and operator, okay? So when we do island in with the bitwise and operator of the health mask, basically we're going to get the last 3 bits. Now, everything else in this health mask is automatically set to be zeros. So that means that all of those values will be ignored, and we're only going to be looking at the like least 3 significant bits. Then we can also go ahead and say like island we can right shift by the number of health bits so that the team is like the lowest bit, right? And then we can end it again with like another binary operator like 0B1, right? And then we, as we said, if the health is greater than 0, we can return the team based on the ordinal value. Otherwise, we're just going to go ahead and return team neutral, because if the health is 0 or if we have some issue, we're just going to return team neutral. Cool. So in the same fashion, let's implement read island location and read maximum island health. Okay, so for island location, I guess let's start with the same code. Let's just copy it over for now. Okay, so our island ID is going to be the same. We're going to read the shared array here, right? And then we need to right shift this down, right? Okay, so how much should we right shift it down by? Yeah, so after this, we're storing like the health and the team, so we can just right shift it down by that much. So it's going to be like the health bits plus the team bits. Cool. And I guess this is like the island index, and then we can just return into location of that. So now we have the map location, and here, let's just say we return, I guess here we can just like return null if we have a game action exception. Well, and finally, let's talk about how we would do team max index help. So this should be very similar to this one here. We can go ahead and just use this health mask, and then we have the health from the health mask, and then we can just return health. And maybe in the case of a game action exception, we can return some error value, like maybe -1 or something like that. Okay. So okay, cool. Okay, so now we've implemented those things. Perfect. So now let's take a look at how we can like start calling this in robot player, right? So some things that we need to do is, so as we talked about at the beginning, so if robot player turn count, we want to update the headquarter info. Then in last lecture, you guys saw that we were using like island nearest loc, and we were just storing it in our static memory, right? But instead here, we can start using our communication array to read the island locations from like all across our different robots, right? So we can start implementing that. Additionally, remember that since we're using a queue, we have to try to write the message at the end of like each robot's turn or somewhere earlier, just because writing messages takes a while. But basically, we want to make sure that we're also like trying to write from the queue. You could also do this a little differently, and every time you push to a queue, just try to write from it. Cool. And then also, like for example, we can start updating the island info when we scan islands. So that's an example of like how you can add it to carrier strategy, and like in the code release, we also might have it added to launcher strategy in a couple places, but that's definitely something you guys should take a look at and make sure it's added in the places you think is good. Okay, and finally, like we'll just end this lecture by talking a little bit about amplifiers. So we've done an entire lecture about communication, but we haven't talked about the robot that's involved in communication the most. So amplifiers, I think I'm not going to spend a lot of time on amplifiers because you guys can code that logic for yourself to see where your amplifiers want to go. But the basic idea of the amplifiers is that queue we discussed earlier. The amplifiers are just going to let us write from the queue faster, right? So if your amplifier is around your robots who are writing to the queue a lot, then we want to add an amplifier there so that they can like send out their messages back to the original, right? So maybe some good places to send them is when we're writing a lot of messages. So right now we're writing messages around enemy robots, we're writing messages around islands, and those are like the main ones, right? So maybe we want to send our amplifiers like near the battle, maybe not exactly into the battle just so they don't die, but near the battle. Maybe we could send them near islands that are contested to give our like headquarters and other units regular updates about like what is happening around those islands and like how we could maybe help that battle. And also maybe we just want to send amplifiers around a little to like explore the area, kind of see if there are enemies in different types of locations. So yeah, I guess that concludes the communication part of the lecture, and I'll definitely release the code tonight, but hope that was helpful for thinking about things. Okay, I'll pass it off to Ian. Do you need me to switch it up?
No, it should be fine.
Just switch it.
Okay. One sec.
Oh, you're good.
Oh, okay, never mind. We're good. So I'm gonna try not to fry your brain too much because I know that was just like a ton of information. But pathfinding, we have locations, we just communicated them. How do we get to our path? So I don't know if you guys have like run your bots yet, but a common issue arises in like one of the maps in particular. Does anyone like know what I'm talking about in this image? Like, does anyone see like what's something that's possibly going wrong here? Anybody? I'm talking about like two blue carriers in the middle of the map. Does anyone know like what they're trying to do and what's wrong with it?
They're trying to get to the well.
Yeah, so basically what this code is probably doing is it's probably sensing a well, and if it sees a well, it's going to go, it finds the direction to it and it tries to move in that direction. But it can't do that. There's a wall straight in the way, and what they often end up doing is just like colliding with the wall and then just like staying there and then just like moving around. Eventually it might like randomly find like the well, but we want to fix that. We want it to like actually find its way to the well. So then other issues that are like similar to this is like, even if it's not a wall, you can be blocked by another robot of your own team trying to go back along the same path. If you're trying to go like from the headquarters directly up to the wall in like this picture, if you go on the current, it's gonna push you down at the end of your turn. So then you're gonna end up with another situation where you go onto the current, you get pushed back, and then you keep trying to go back onto the current. and you keep getting pushed back. And then your robot's just gonna get stuck. So we're gonna do some like pathfinding algorithms. The bread and butter is like the BFS, the breadth first search. So basically you're gonna start at like your location and you can see every location that's like visible, like that you can reach in one more move. And then you keep doing that, you keep track of like the shortest path to each location you visited. It's like in this GIF I found, like you start on the bottom right and you're trying to get to the bottom to the top left. And like you've seen like all the locations you can find in one move, in two moves, in three moves, and so on. And so that involves like looping through basically every location. And that's gonna use like a lot of bytecode. And it's not optimal if like you spend 5 turns calculating the path, but it's only like slightly better than what you would have done by just like moving randomly, basically. So you can try like saving bytecode. You can do this by like not investigating every path, but like only paths like that go forwards or like to the left or right slightly. You can try like distributing the computation of like other robots and using communication somehow. That seems a bit complex though, and I'll leave you guys to like consider that. There's also small like bytecode optimizations, which we'll talk about in a future lecture. But what we're actually are going to use this lecture is like a pathfinding that's like a bit less optimal. It's not always going to find you the shortest path, but it's more useful because it requires like less computation. So what we're going to be talking about is like, it's called bug nav, because it's like a bug trying to move from one location to another. And it uses like local knowledge of like what it can directly see around it. I'm going to shamelessly copy like pictures and resources from these 2 links. So if you're at all interested, you can just like look up bug nav or like bug pathfinding algorithms, something like that. And you should find these 2 links, or you can come up and I'll like send them to you. But the first like variant is like bug zero algorithm. It is basically you have your location and you have a goal location. And you're just going to keep trying to head directly from your location to the goal location. And every time you encounter an obstacle, which can be like a wall, a current going the opposite direction, or like even another robot, you're just going to turn to the left until you can keep heading in that direction. And you just keep doing that. So that seems pretty straightforward. Basically, you're going to keep going in the direction you want until you find an issue, and then you just go to the left or go to the right until the issue is gone. However, that doesn't like always end up finding the goal. For example, in this here, it's gonna go like, I should hide it so you can actually see. Okay, what it's gonna try doing is it's gonna try going straight up. It's gonna find the obstacle. It goes to the left, and then it's gonna be like, can you see my mouse? Yeah, it's gonna be like about here, and it's gonna try to go to the goal, and then encounters the obstacle again. And then when it goes to the left on this obstacle, and it's just like looping around until it goes back to the beginning. So bug nav is like a good heuristic to like help you get around obstacles. Well, like bug zero is a good heuristic to get around obstacles. But then in certain situations, like if you make a map that looks like a maze, it's gonna end up just like looping around sometimes. So there's like other variants that are a bit more complex. We have bug 1, which is like after you see an obstacle, you're gonna like go all the way around it, and you're gonna find like the closest point you can get to the obstacle, and you're gonna remember that. It's like and then you're gonna go back to this like closest point. So in this example, like you go straight, you find an obstacle, and you go around it, and then you see like this blue dot. That's the closest point to the goal. So you go back to the blue dot, and then you go straight up, find another obstacle, go all the way around it, and then you find this blue dot, and then eventually you go back there and you go straight to the goal. Like going all the way around the obstacle might seem like a bit excessive, and in some cases it might be. But if you're going like repeatedly back and forth, for example, like between a wall and a head corner, it might be worth it to like spend 1 turn or just spend a few turns for the first trip, finding like the optimal path, so that in future trips you're taking the most efficient path. Or like if one robot finds the most efficient path, they could try communicating like this closest point so that other robots can use it for their paths. You can also go like further. There's bug 2, which basically you're gonna draw a line between like your current location and the goal location. It's like here's the start and here's the goal. And you're gonna navigate around the obstacle until you intersect this line again, closer to the goal. But it seems like a bit complex to implement. So it might not be worth it, but it's just something to consider, like an idea you might want to think about. For now, we're gonna attempt doing an implementation of bug 0. And if you want, you can try doing bug 1 or bug 2 on your own time. Okay. And I will hand it off to Jerry.
All right, cool. Hello. So what's going to be happening now is we're going to attempt to code bug 0 together to sort of get a sense for how we can implement this pathing algorithm together. Cool. I'm going to leave the webcam on actually in the corner so people in the stream might be able to see me. But in the meantime, let's head back to the code. And what we're going to do is we're going to just start with a fresh copy of lecture player as it was before the communication stuff. So I'm just going to sort of put us back into where we were. So switch to master as well, has been told. Whoops. Cool. So what we're going to do is we're actually going to implement this communication stuff together. See a communication. So we have communication to Java. So what we're going to do is we're going to create a new file here. We're going to call this file. We're in the right place. Yes, we are. We're going to call this pathing.java. So we're going to be implementing pathing together in this folder. What we're going to be doing is we're going to be implementing this basic idea of bug nav. It's going to be bug version 0. Cool. So let's get started with some sort of boilerplate that we'll definitely need. Let's say we create a function that says move towards something that sort of makes sense. We'll need the robot controller to be able to move. And we're also going to say we're going to ask for a target. And potentially this could throw an exception. This is going to be the function that we're going to be implementing. So we're going to be implementing this method, which lets us move towards some arbitrary target. So sort of a couple things to get ourselves started. First of all, let's detect our current location, because that's probably pretty important. If we want to be moving towards somewhere, we want to know where we are right now. So let's get our current location. And potentially this could equal the target. What do we do if it is the target? What if the current location is equal to the target? Any suggestions for what we can do? Do we have no suggestions? Yes. That's great. So we're already there, so we can just return. So that's exactly what we're going to do. So if we're already at the location, we can just sort of be done. Otherwise, we're not at the target yet. So now what this means is we actually have to think about what we want to do, how we're actually going to get to the target. First of all, we're just going to add a quick sort of sanity check. If we have too much cooldown, we're not ready to move, then we can also return because sort of anything we calculate won't be helpful. We are not ready to move towards there yet. Otherwise, we can actually start thinking about how we're going to get there. So let's create a direction, which is the direction we're going to be wanting to move in. We're going to take our current location. And we're going to get the direction to the target. This is the direction that we're going to try to move in. Because if we can move in that direction, so there's a couple things that we have to be able to check to be able to. So if we can move in that direction, we can just directly go ahead and do that move. If we can move in that direction, we can just go ahead and do it. The interesting thing happens when we can't move in that direction. Because when we can't move in that direction, we have to think about sort of this idea of our original bug nav, right? So the idea of bug nav was when you can't move in the direction, you can just sort of move in it. But then when you can't move in the direction, you sort of want to do this idea of sort of going around the object. So this part of here is exactly where we're going to be talking about this idea of going around some obstacle, right? Because if we can't move in that, we can't move towards D because there's an obstacle there. So this is the part where we actually have to think about how to move around this obstacle. Any questions so far? Great. So given that there's an obstacle here, we're gonna have to start thinking about how to move around it. The way we're going to actually do this is, let's actually think about what it means to walk around an obstacle sort of in real life. And in real life, let's suppose, for example, that let's say we're going to try to go around an obstacle clockwise. So you're on, say, like you've got the obstacle on your right hand side, on your right hand, and sort of keep on walking forward, and you're going to keep the obstacle on your right hand. So what this means is you're going to sort of keep on trying to go forward, but if you can turn right, you're going to do that as soon as you can. But if you can't turn right, then you're going to sort of like try to go forward. But if the obstacle sort of curves around in front of you, then you're going to turn left. And that's the sort of the idea we're going to go for. So we're going to take the idea of trying to keep the obstacle on our right hand. So this is going to look like this. We're going to remember where our hand is pointing by keeping track of our current direction, which is the direction that we're currently trying to move in. The idea is what we're going to say is we're going to try to move in this direction, but also try to turn right whenever we can, because this is the idea of sort of keeping the obstacle on our right hand. So we're going to say, first of all, if we don't have a current direction, then our current direction is going to now take on this direction that our target is. We're going to take on this target direction D by setting a current direction to it. And now, essentially, we're going to just kind of try this idea of moving towards the current direction. But if we can't, we're going to like try to move in a way that keeps the obstacle on our right. And we can do that by essentially saying, well, if we can move in this direction, if we can move in it, then we can move. But what if we can't move in that direction? That means the obstacle is sort of like right in front of us. And if it's right in front of us, then the way we sort of keep it on our right-hand side is we have to sort of take a left sort of turn, right? If the obstacle is right in front of you, then to keep it on your right hand, you take a left turn. And now the obstacle will be on your right hand. So if you can't do that, you're going to take the current direction. If you can't do that, you're going to take the current direction and you're actually going to rotate it to the left. Right, so if you can't do that, you're going to rotate it to the left. But once you've actually done this rotation, you can have another shot at moving. You can actually sort of have another shot at moving. So you can imagine copy pasting this code, right? You could say, well, if I can move in this direction, I'm going to move in it. Otherwise, I'm going to take a left turn and try again to move in it. And otherwise, I'm going to try to take another left turn and move in that direction. And at this point, you might realize that it might be better to actually have written this code in a loop. So we're going to sort of remove all of that, copy paste, remove all of that, copy paste. And wrap this in a loop. We're going to try all 8 directions. I'm going to try to repeat this 8 times. I'm going to repeat this 8 times. Set it in that. Great, cool. So the idea here is what we're essentially saying is, well, we're going to try to move in our current direction. But if there's an obstacle right in front of us, then to keep the obstacle on our right hand, what we're going to do is we're going to turn left. And finally, once we do succeed in moving, we can actually break out of this loop. We can break out of this loop. the last thing you actually have to do to make sure that this code really works is once you take a step forward, you also have to check, what if the obstacle is curving away from you? If it's curving away from you, then to sort of be able to keep it on your right hand, you also have to turn in towards the obstacle. So the last thing we do is we turn in towards the obstacle. So to turn in towards it, you turn right at this step here. That's actually most of BugNav. The last thing you also need to do is also that once you do get to move successfully, you can actually reset your current direction, because what this being able to move successfully here means that there is no obstacle we're going around. Are there any questions so far about what this code is doing? We're probably not going to be staring at this code much longer, so if you have questions, now is a really good time to ask. Okay, great. There's a lot of errors here. That's because we haven't imported the things we need to import. Cool. And current direction. Cool. So given this, we can actually try to apply it somewhere. So let's come back to the carrier strategy and look at where we can try to apply this. Well, one place we can try to apply this is, well, if we're in the anchor mode, then instead of sort of blindly moving towards the location of an island, this looks like we still have the communication stuff in here, but that's fine. Well, instead of sort of blindly moving towards the island, what we can do is we can actually use this pathing that we've just written, because we can use that to sort of navigate around the obstacles instead of just sort of moving forward and encountering the issues that Ian sort of highlighted to us before. So the way we can do this is we can say, well, instead of robot player.move towards, we can replace this with our new pathing code, which says, what was the function that we called? Pathing.move towards. So we're going to call it pathing.move towards RC and island marker. And then this pathing.move towards will hopefully do exactly what we want to do. So it will hopefully take us toward the island while actually navigating around any obstacles. Cool. So hopefully this code actually works. Let's give it a run. We'll see what happens. Gradle run. Let's say we're gonna list command prompt. I've been told command prompt. Let's run lecture player, and to keep things clean, we're just going to run this against the example function player, and we're also going to keep things quiet, so not too much Java. Cool. So this is now compiling. It's running. Oh, we have a new version. That's fine. So while that runs, one last chance to ask questions. Read the code here again. It's a bit of a long game, this one is. Default map is a big map, I guess. All right, so we can actually try to watch this game. Where is the client? We have a client. Okay, so we can try to watch this game. So do I have to upload a replay file here? Yep. Cool. So let's check. This one here, I think, is the one we just made. So is that this one? I think it is this one. So we can hopefully see lecture player pathing towards the islands. So if we go back a bit, if we sort of just scroll forward a bit, see the times when the islands get taken over. Does it take over the islands? Okay, it seems like the islands in this one get taken over right at the start. So let's sort of watch that bit of the pathing. So, for example, we can see this carrier here sort of takes a pretty straight path straight towards the island. We sort of don't have maps that show this obstacle behavior, but the code actually does implement that quite successfully as well. So if you do encounter obstacles on your way to the island, that is handled by the code. So that pretty much wraps up the implementation of BugNav. So BugNav for bug 0 algorithm. If there's any questions about pathing or communication or about your bot in general, feel free to stick around and we'll answer any questions about that. But for now, that's pretty much all we have for the lecture. So thanks for coming.
I